Welcome to OP's Math e-Pathshala.
Direct product of groups. So this idea came from our intention to construct new groups from the old ones. So that is, we need to construct new groups from the old ones. For instance, for example, given a group, one may construct its automorphism group. Automorphism group. So in this section, we see that this is another important way of construction of new groups from the old ones. And if we go further in finite group theory, then we will see that this operation has important role in finite group theory, because every finite abelian group can be made isomorphic to direct product of cyclic groups. So that is an important observation and important application of direct products in group theory. So let us start with the construction of direct products between two groups. How could it be done? So let us start by considering two groups, G1 and G2. Now set G equals to the Cartesian product of these two. That means it contains the set of all those elements G1, G2. So all those order pairs where G1 belongs to capital G1 and G2 belongs to capital G2. So we consider this set G. Now to make it a group, we need to define a binary operation on G with the help of the binary operations respectively on G1 and on G2. So let us define a binary operation dot on G by. So now pick two elements from G. So G1 G2 dot G1 dashed G2 dashed. So consider two elements from G. Now we define the operation as so G1 G2 dot G1 dash G2 dashed. So it is defined to be the element which is G1 G1 dashed and G2 G2 dashed. Now let us check. Now since they are associative, so they satisfy associativity. G is also associative with respect to. Now for the identity, now we know that G1 has the identity, suppose it is E1, G2 has the identity, suppose E2. Then we define an element, so let E is E1, E2, which is in G. So E is E1, E2, which is in G. Now we need to check whether it is the identity or not of the set of this G with respect to the defined dot. So for that reason, so let G1, G2 be any element of G. Then G1, G2 dot E1, E2. Then it is G1, E1, it is G2, E2. Now since E1 and E2 are the identity elements of the respective groups G1 and G2, so this must be G1, G2. In a similar way, we can show that E1, E2 dot G1, G2 is also G1, G2. And this proves that E is the identity of G with respect to dot. Yeah. So this is the identity. Now it remains to check the existence of inverse for each element of the set G with respect to the operation dot. And suppose again G1, G2 be any element of G. So G1 belongs to G1, capital G1, and G2 belongs to capital G2, which implies that G1 inverse belongs to G1, G2 inverse belongs to G2. That is, the inverse of G1 and G2 will exist in the respective groups. So then G1, G2 dot G1 inverse, G2 inverse. So it is G1, G1 inverse, it is G2, G2 inverse. So therefore it is E1, it is E2, so it is E. And similarly, just do it from the other side. So it would be again E1, E2. So this proves that, so this implies the inverse of G1, G2 is G1 inverse, G2 inverse, which is again in G. So thus, the defined set G forms a group with respect to the operation dot. And this group is called the external direct product of G1, G2. So this G is called external direct product of the two groups G1 and G2. So that is, if you have two groups G1 and G2, then you can construct another group from G1 and G2 with the help of their operations. And this is very much easy. Now you can go further with the same technique for finitely many groups. That is, given any finitely many groups, suppose n number of groups G1, G2, Gn, suppose if we consider finitely many groups G1, G2, Gn, suppose n number of groups are there, then using the same procedure, one can construct the group G with respect to the dot, the binary operation, dot defined by G1, G2, Gn dot G1 dashed, G2 dashed, Gn dashed. So the definition is, it is component wise, that is G1, G1 dashed, G2, G2 dashed, Gn, Gn dashed. And the operations here, here and here are the respective operations of the respective groups G1, capital G2, capital Gn. So in the same way, we can show that this G is also a group with respect to this operation. And this will be called the external direct product of, so this will be called the external direct product of G1, G2, G3 and Gn. External direct product of finitely many groups. Now, one thing you can observe is that if G1, G2, Gn, each of these groups are abelian, then so is their direct product. So one can observe that if GKs are abelian, then so is their external direct product. G1 cross G2 cross Gn. Now one may denote the external direct product of G1, G2, Gn as this, k equals to 1 to n. And if we consider abelian groups, then some authors are preferred to use the notation Gk, k equals to 1 to this. That is sum of G1, G2, Gn. So this notation is also familiar for direct products of abelian groups. Now let us move on to another important observation which can be listed by some statements for the subgroups of a group. That is, if we are given finitely many subgroups, that is suppose H1, H2, Hn of some group G, then some statements are equivalent. What are those? So let us state the theorem first. That now we consider subgroups of a group Hk, H1, H2, Hk. So these are all subgroups of a group G, and let H is this one, H1, H2, Hk. Then the following are equivalent. Are equivalent. What are the statements? The first one is this H will be isomorphic to the external direct product of these k subgroups. That is, H is isomorphic to H1 cross H2 cross Hk. Now since H1, H2, Hk being subgroups, so these are itself a group, and so we may consider their external direct products. If their external direct product it is isomorphic to H. So this is our first statement. Because how do we construct this isomorphism? Actually, if we are given H1, H2, Hk, then one may consider a map. That is the map. What is the map? Let us have a look. The map phi colon H1 cross H2 cross HK towards H by the rule phi of H1 H2 HK goes to their product. Yeah. So if you consider k number of subgroups H1 H2 HK, then you may have this map phi from H1 cross H2 cross HK, the external direct product of these groups, towards the H. Now our statement is that this map is an isomorphism. Isomorphism from the direct product of H1 H2 HK onto this product, the internal direct product of this, internal product you may say, H1 H2 HK. So this is our first statement. Now the second one is that for all I equals to 1 to k, each one is normal in H. That is, each subgroup is a normal subgroup in H. And in addition to this, each member of that H can be uniquely represented as the internal product of H1 H2 HK, where each HI belongs to their respective groups, capital HI. So this is our second statement. Third one is that for all I equals to 1 to k, these HIs are normals in H, and if the internal product H1 H2 HK, if it is identity, then the only possibility is that H1 H2 HKs, all of them are equals to E. So that is the only possibility. This is the third statement. And the fourth one is that for all I equals to 1 to k, HI is normal in H, and HI intersection, the internal product of H1 H2 HI minus 1 HI plus 1 dot 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 HK. That is, take out just the HI and then just doing the product, internal product of the other groups. that is H1, H2, Hi minus 1, Hi plus 1, Hk. So intersection of Hi with this one must be identity. So this is our statements, and we shall prove that each one will imply the other. That is, the following are equivalent. So let us first check that 1 will imply 2. That is, suppose 1 is true. One is true. So then, now define a map psi colon H2 H1 cross H2 cross Hi minus 1, and just consider the ith group only, the trivial group identity, and then again proceed as before. Hk. Just putting the ith group as a trivial group, and then the definition will be of this map will be the psi of H1 H2 Hi minus 1 Hi Hi plus 1 Hk. So this element will go to H1 H2 Hi minus 1 and just put in the ith place identity, and then proceed as before. This. So you can define this map. Now suppose 1 is true. Now suppose 1 is true. So what is 1? That is, this map is an isomorphism. This map is an isomorphism. So let us check so our intention is to prove that 2. So this is our goal. That is, each Hi is normally in H, and each x can be represented uniquely as x equal to the internal product H1 H2 Hk.
Thanks for watching. Please subscribe, like and share.